All right, so I told you I get excited when we have unit equations, a statement of two things being equal, because from that we get unit factors, which equal 1. That means we can multiply, divide all day long, and it doesn't alter anything but units. And we have to do that with atoms because we can't see atoms. So we must use their masses to count them. They're too small and too numerous to count individually. Even if you see atoms and counted them 24 hours a day, as long as you lived, you'd barely begin to count the number of atoms in something as small as a grain of sand. So when I say dozen, what do you think?
12. 8.
When I say baker's dozen, what do you think?
13.
When I say a case, what do you think?
24.
All right.
I didn't know a case, I'm sorry.
I took a guess.
All right, so we have these words that mean larger numbers, and we're going to do the same thing here. 1 mole of things is 6.022 times 10 to the 23rd of those things. So that's quite a big number. A lot of trailing zeros there. 1 mole of anything is Avogadro's number of that thing, 6.022 times 10 to the 23rd. So Avogadro came up with this number. 1 mole of marbles corresponds to 6.022 times 10 to the 23rd marbles. 1 mole of grain of sand is 6.02 times 10 to the 23rd grains of sand. Well, we're not interested in marbles and grains of sand so much, but here is roughly 1 mole of copper atoms. And that looks like an amount we could weigh out. And of course, these are copper pennies pre-1982 that are solid copper, not the ones nowadays that are mostly zinc and just copper coated. Here's 2 large helium balloons. That's approximately 1 mole of helium. So where did we come up with some of these numbers? The numerical value of the mole is defined as being equal to the number of atoms in exactly 12 grams of pure carbon 12. Or I might have said earlier that 1 atom of carbon 12 weighs exactly 12 AMUs, atomic mass units. And we can move from atomic mass units to grams pretty easily. This definition establishes a relationship between mass in grams of carbon and the number of atoms, Avogadro's number. And this relationship allows us to count atoms by weighing them. So if we have 3.5 moles of helium, we want to know how many number of helium atoms are there. Here is a unit equation. 1 mole of helium is Avogadro's number of helium atoms. And from this unit equation, we come up with a unit factor. And it turns out we're going to multiply by Avogadro's number. If we know the moles of something and we want to calculate the number of particles, we multiply by Avogadro's number. And you can see moles of helium canceling out, and we end up with a number of helium atoms. Anybody walk in late and not get a mole map? So that first example problem said 3.5 moles of helium. How many helium atoms is that? And so we multiply this way and we get to number of particles. Instead of A, we're saying helium. And we go this way. And we're going to learn this to do a lot of things in chemistry. Like if we know the mass of one reactant, how much mass of the other reactant do we need? Or how much mass of product based on that reactant? Should be fairly useful. Now we're going to go the other way. So now I have 1.1 times 10 to the 22 silver atoms. Find the moles of silver. So I use the reciprocal. I can still write 1 mole of silver equals 6.022 times 10 to the 23rd silver atoms. So every unit equation has 2 unit factors. And so notice now we divide by Avogadro's number. Now there's one common, easy way to mess this up. You know the concept. How many of you have become intimate with your calculator? Raise your hand. I got to work on everybody. So if you go like this and hit enter, you won't have any trouble. One way to run into trouble, I don't like to write it down because students might copy me, is using that caret key. And then the student might want to do this. Now watch what happens when I do this. If I go 1.1 times 10 caret 22, this gives me 1 point something times 10 to the, 44th. So the order of operations, it does this. So if you want to use your caret, you got to parenthesize this off. But I suggest you just get used to using the E key and do it like this, because this ties it all together. That does this. If I do the E key, I'm going to go 1.1, hit the E key, 22, divide 6.022 E key, 23, and I get this answer. Only not as irritating, maybe, which is this thing here. See, this number and this number are the same. This is just scientific notation. All right, so this gets you the right answer. This is the right answer. Using the caret is problematic. Now, it's not problematic if you do it like this, but I got big fat fingers. That's why I like a classical guitar, the neck's wider. Yeah, so become intimate with your calculator. It'll help you get better grades. So these things illustrate why a mole is helpful, perhaps. I used to bring in a beaker of marbles and a beaker of ping pong balls and say, will a kilogram of both deliver the same amount? And students would say no. Then I'd say, well, how about a liter of both? And they say no, because everything weighed different and had different volumes. And here, these are going to weigh different, and they're going to have different volumes. These pictures have the same number of nails. The weight of 1 dozen changes for different nails, and they also have different volumes. These pictures have the same number of atoms. The weight of 1 mole of atoms change for different elements. Here's 1 mole of sulfur, and you might have noticed the label in Lab 5. I grabbed my mole display for sulfur. This looks like a lump of coal. 1 mole of carbon. And you'll notice the number you see up on the periodic table. If you look up at carbon on the periodic table, you're going to see 12.011 roughly. So here's what I just said 10 minutes ago. The atomic mass unit, AMU, is defined as 1/12 the mass of a carbon 12 atom. We're saying a carbon 12 atom weighs exactly 12 atomic mass units. The molar mass of any element is the mass of 1 mole of atoms of that element, and it turns out is equal to the atomic mass of that element just expressed in AMUs. Or if you know the AMUs and you just turn it around to grams. So here, 1 copper atom has an atomic mass of 63.55 atomic mass units. And I'm going to say, no, it doesn't, because you have some different isotopes. On average, a copper atom is going to weigh that amount. So now if I take the AMUs away and put a gram, I can actually go grams per mole. And when I get to this point, you should get excited and say, oh, I see how this works. Always when you see a slash, your chemistry instructor, if it's me, says, make that look like a unit factor. 1 mole of Cu, that almost looks like calcium. Let me fix that up. 1 mole of copper is that many grams. That also contains Avogadro's number. So when I have a mole map, let's just say I have 5 grams of copper, and I multiply by something that says 1 mole of copper is equal to 60, almost, let me get the full 63.55 looks good. If I pull out my calculator right now, I'm going to know moles of copper. If I multiply by another unit factor that says 6.022 times 10 to the 23rd. Let's see what that equals. Let's see how many copper atoms are in 5 grams of copper. So I go 5 grams. I'm right here. And I'm multiplying this thing that says 1 mole of something over its molar mass. In this case, 1 mole of copper over 63.55. So here we go, divide 63.55. And then I'm gonna multiply by something. 6.022 times 10 to the 23rd. I'm getting lazy, so I'm gonna start rounding. So notice what happened. Let me leave that up there if you're, boy, it's all washed out. You can hardly see it. So notice what we did. We started out with mass of copper. When we divided by copper's molar mass, which is multiplying by this reciprocal, notice what unit canceled. Grams of copper canceled, and if that's all I did, I'd now know moles of copper. And then when I multiply by Avogadro's number, I come up here with number of particles. How many of you want to upgrade your mole map? I should upgrade it. We can put 1 mole of A, 6.022 times 10 to the 23rd particles, and that will take us in that direction. So we can have particles and find moles, and we can find mass, or we can go mass, particles, or we can go to other reactants and products. Fascinating. The mass of 1 mole of elements changes for different elements. We can get these off the periodic table. That's why they're so useful. The lighter the atom, the less mass in 1 mole of that atom. So lithium, roughly a little less than 7 grams, I got 1 mole. Sulfur, however, I need 32.07 grams to get a mole. So now you know the definition of molar mass. And when you see it given to you, it'll say 12.011 grams of sulfur per mole. So you normally get it kind of in the unit factor form. All right, calculate the number of moles of sulfur in 57 grams of sulfur. I'm gonna pull out the chemist's most important tool, periodic table. Now you know why, no more mysteries. And I'm gonna just start up here. And everything proceeds through the mole. Now students, many times they get excited and they pull out Avogadro's number. I don't need that yet. I wanna find sulfur and go 32.07 grams of sulfur. So I've converted mass of sulfur into moles of sulfur. Here's a unit I need to get rid of. So I gotta put that in the bottom. Pull out my calculator. Oh, I got so excited I went the next step. How many moles? All right, well, we're just gonna forget that part for right now. 57.8 divide 32.07. Rounding to 3 digits, we'd round this way. Now, if I multiply this number by Avogadro's number, we could find the number of particles if we needed to. Any questions? Oh, let me not photobomb your picture. So I just skipped a couple slides to get to an example problem like I was trying to do. Calculate the number of aluminum atoms that are in 16.2 grams of aluminum. So we want to take this and convert it into moles. 1 mole of aluminum, look up at the periodic table, almost 27. So if we just wanted to find moles, we'd stop there. Now the unit of mole aluminum cancels, and we end up with this many aluminum atoms.